Hello my dear students. While considering the preparation of JEE, definitely the previous year questions and the study based on that, it is very important. And if the pattern of questions, that also if it is predictable, then it is super easy, right? So in today's video, we are going to do the in detail recap theoretical discussion of such three chapters, that is properties of solids, properties of fluids and kinetic theory of gases. Welcome to another episode of JEE Mantra 2025 by Brilliant Khatar. So here comes the very first chapter for you, that is properties of solids. Okay, here first on the very first slide we are having deforming force, elasticity and elastic limit. Now before starting the theoretical part, the discussion, I would like to tell you one thing. In this particular chapter we will be discussing many definitions. Okay, conventionally it was never there for other chapters that we discussed so far in the last 6 videos, but here we will be discussing about the definitions and few theoretical points, because as I told you in the beginning itself, if we can identify the pattern of the questions, things are going to be super easy, right? Here in this particular, related to this particular chapter, that is properties of solids, especially in the assertion and reason type questions as well as match the following type of questions. Okay, there these definitions and the theoretical detail associated to those terminologies were very important, and that was frequently asked. So that is why ever never skip that details, because this particular video is framed based on those PYQs only. Okay, so we tried our best to include all the points which were there in the PYQs. Okay, so that's why I am telling, ever never think that this theoretical explanation is useless. No, it will be helpful. You can check the same after going through the video. Just go through the questions and try to solve that. There you will get what I mean to say. All right, so as I told in the beginning, we are having deforming force, elasticity and elastic limit. Okay, so here deforming force is any particular force that applied onto a body which can cause a change in shape of the object, that is deforming force. And elasticity, you know that is the property of any particular material. Once the deforming force is removed, I repeat, once the deforming force is removed, that particular material can come back to its original size and shape. That is, that the name of that property is known as what? Elasticity. All right, and next is elastic limit. Okay, that is the upper limit of deforming force. Upper limit of deforming force within which the elastic property of the material is retained. Okay, and if you increase the force beyond the elastic limit, then the elastic property or elasticity of the material will be vanished. Okay, that the material will lose that particular property. So the maximum limit of the deforming force within which the body maintain its elasticity is known as what? Elastic limit. Okay, so the name itself, the things are there. Okay, now remember one thing again, these definitions, it's if you can create your own, some tips, some techniques to easily memorize all these things, okay, recollect all these things, that will be the best thing ever possible. All right, so that particular part also need to be there in your priority. You must have your own techniques to memorize all these definitions, terminologies and equations. Okay, so elastic limit means that means it is a limit related to elasticity. Okay, so beyond that limit, elastic property won't be there. Okay, in that way you can connect the thing. Going to the next, it is perfectly elastic bodies and perfectly plastic bodies. Now how you need to compare this one is, here it is perfectly plastic body and there it is elastic body. Okay, so the one which is not elastic, that is plastic. Okay, so what was elastic? Once the force is removed, it can regain its shape. So the one which cannot do so, that is known as what? That is known as plastic. Okay, there itself an add-on word is there, that is perfectly elastic and perfectly plastic. So perfectly elastic and perfectly plastic means once the force is being removed, the body will be having the tendency to go back to its original shape. So if any body perfectly go back to its initial shape, that is known as what? Perfectly elastic. And deformation is done, and even the body don't even make an attempt to go back to its original position. That is known as what? Perfectly plastic. So the one which want to go back to its initial state at 100% accuracy, that is known as what? Perfectly elastic. And the one which don't even want to think of it, you can precise like you can connect in that way, that is known as what? Perfectly plastic body. Okay, now it is stress. Here of course you must know what is stress. Other than that, you must know the dimensional formula, because stress related dimensional formula were asked many a times, especially in the chapter units and dimensions. And other than that, about its nature, whether it is a scalar, vector or tensor quantity, in that way also. So 3 points are there associated to this particular topic. That one is stress. So let's see what you mean by a stress. So let this be an object, okay, and here I am applying an external force. I am applying an external force, and this external force is that deforming force. So once an external deforming force is applied, okay, so there will be a tendency of the body to come back to its original shape. I already told you, okay, and that tendency is what? Elasticity. That property is known as what? Elasticity. Now the force acting in the opposite direction, this force is known as restoring force, and the restoring force act perpendicular to the surface. It's not mandatory that all the time the restoring force need to be perpendicular. It can be inclined also. That depends upon in which direction the force is being acting, okay, or sometimes it depends on the shape of the body also, okay. So if the restoring force acting normal to the surface is F and A is the area, then force acting per area, that is known as what? The stress. Okay, restoring force acting perpendicular to the area, restoring force acting perpendicular to the area, perpendicular to the area upon the area, that is a stress. And there itself I prefer to call it as normal stress. Okay, now you might be wondering, what if a horizontal component is also there? So definitely we will be discussing about that. So in short, restoring force upon the area, that is known as what? That is known as stress. And there itself, if the force is acting perpendicular, then we will call it as what? Normal stress. Okay, and I told you regarding the tangential force, we will be discussing it later on. Now as it is force upon area, it's going to have the same unit as well as dimension as that of pressure, that is Newton per meter square, and the unit is what? Pascal. And dimensional formula is going to be same as that of pressure, that is ml raised to minus 1 t raised to minus 2, and it's not a scalar quantity, it's not a vector quantity, but it is a tensor quantity. Okay, the next one is normal stress, volumetric stress and tangential stress. The last slide I told you about normal stress, and there I triggered a case. What was that? What if the force is tangential? So that particular point is going to be addressed here. Okay, so let's dive into the deep discussion again for the same, all these 3 points, that is normal, volumetric as well as tangential stress. So normal stress we already discussed. If the force acting is normal to a particular surface, there we call it as what? Normal stress. Okay, force upon area, that is known as normal stress. So let's consider one example, like let this be a rod and I am applying a force like this. Okay, so here this is the surface and the force acting is what? Normal to that. So here force upon area, we call it as what? Normal stress. We call it as what? Normal stress. So here in this case, what will be the tendency? the tendency of the body is to increase its length. Okay, so here we call this as tensile stress. What we call? We call it as tensile stress. And if the force is acting like this, here the force is trying to compress the body. There we call it as what? Compressive stress. We call it as compressive stress. Okay, so in both the case, force is acting normal. Now what we have is volumetric stress. So here in this case, what happens? Let me consider a spherical volume. It's not mandatory that it to be spherical, it can be cubical also. And if normal force is acting on from all the direction onto the surface, then the total force acting. So if let F be the force acting, okay, now this force F acting upon its surface area, that's going to be what? 4 pi r square. Okay, it's acting from all the surface. Then we call it as what? Volumetric stress. Volumetric stress. We call this as volumetric stress. Okay, and next comes tangential stress. Okay, there I told you, let's consider a case like this. Let this be a body kept on a surface. Okay, let this be fixed or attached to another surface like this. Now let me apply a force like this. Let me apply a force like this and let this angle be theta. Now you know that definitely if the external force is acting at an inclined direction like this, the restoring force is also supposed to what? Act in this direction. Okay, now this particular force is going to have F sin theta component here like this and F cos theta component this way. As a result, definitely the restoring force also going to have a horizontal component, isn't it, and a vertical component. So of course this vertical component upon area, we call it as what? Normal stress. But here you can see a tangential force. Now this tangential force or the horizontal force, you can call this as tangential force or the horizontal force upon area. Okay, that we call it as what? Tangential stress. I hope you got it. Okay, so here this was normal stress, two possibilities, tensile stress as well as compressive stress, and here also what? Next one, that was volumetric stress. So here also the volume to get decreased as well as the volume to get increased, both the possibilities are there, not only here, possibilities are here also. And the next one was tangential stress. So for the tangential stress to act, definitely the force must be acting at a direction inclined to the surface of contact. So that is a mandatory part over there. Alright, so normal stress, normal stress, volumetric stress and tangential stress, these 3 points are clear for you, I believe. Now I am taking you to the next one, that is strain. Okay, basically strain means fractional change in configuration. That is the first line definition for strain. Okay, that is fractional change in configuration. Now the questions, what could be the configurational change possible? It could be change in length, it could be change in volume, isn't it? Fine. So there the first thing coming is longitudinal strain. So definition itself says what? Fractional change, isn't it? So if it is longitudinal strain, definitely here this is going to be what? Change in length upon original length. Okay, don't get confused. Here this is delta L, change in length upon original length. Next is volumetric strain. That is change in volume upon original volume. Okay, the next one is shearing strain. What it is? Shearing strain. So for longitudinal strain as well as volumetric strain, I repeat, for longitudinal strain as well as volumetric strain, for longitudinal strain normal stress is sufficient, volumetric strain also that normal stress is sufficient, but in case of shearing strain we need tangential stress. Okay, now how it happens? Let me consider an arrangement like this. The bottom portion is fixed and let me apply a force in this manner. So if I apply a force like this, a deformation can be predicted and that deformation is going to be something like this. So this is the deformation that happened. Okay, now here this was the actual shape and now the deformation happened in this way. Now let this angle be d theta. Let this angle be d theta and this linear displacement, let me take it as dx and let me take this as y, or you can take it as small letter h. Okay, now we were discussing about what? We were discussing about strain, okay, fractional change. So here this fractional change is going to be delta, not delta, it's dx upon y. It's going to be dx upon y. Okay, now dx upon y is going to be what? This angle included, so it can be marked as what? D theta. And we call this as what? Shear strain. It's going to be shear strain. I hope you got it. So the same definition you can see here. It is the angular displacement of the plane perpendicular to the fixed surface. Let's see whether that particular definition is justified here or not. This is the fixed surface, okay, and this is that perpendicular plane, and this perpendicular plane got displaced to an angle of d theta, and we call that angular displacement as what? Shear strain. Okay, now let me take you back to this particular slide where longitudinal strain, volumetric strain as well as shear strain, all the three were telling about the fractional change only. So since it is telling about the fractional change, once we want to tell about the unit or the dimensional formula, it's supposed to have any unit and it's not supposed to have any dimensional formula also. Okay, so it has no unit and it is a dimensionless quantity. That is also an important point related to all the three terms here. Okay, the next one is Hooke's law. Okay, Hooke's law tells how stress and strain are connected, or how we can predict a relation between these two. This relation is applicable within elastic limit only, and how the relation is stress is directly proportional to strain. Okay, so Hooke's law says within the elastic limit stress is directly proportional to strain. All right, stress is directly proportional to strain within elastic limit. All right, here the proportionality sign is removed by using a proportionality constant, and that proportionality constant is known as what? The modulus of elasticity. Terminologies are very important. It is known as what? Modulus of elasticity. So the modulus of elasticity, capital E, that is the ratio of stress upon strain. Okay, again, strain is unitless, dimensionless physical quantity. So definitely the unit of modulus of elasticity, it need to be same as that of what? Stress only. So the unit as well as the dimensional formula of modulus of elasticity, it's going to be same as that of what? Stress. Okay, I'm telling each and every points regarding each terms that we come across. Okay, all right. Now next one is types of modulus of elasticity. So depending upon the type of deformation, the modulus of elasticity is also classified. Okay, fine. Out of that, the very first one is Young's modulus of elasticity. Okay, Young's modulus of elasticity, and here this is related to longitudinal stress and longitudinal strain. Okay, so what was modulus of elasticity? Is stress upon strain only. Now, since it is related to the length, it's going to be normal stress upon longitudinal strain. And what was longitudinal strain? Change in length upon original length, isn't it? Why? Like after all, it's about what? Fractional change. So fractional change in length, that is what we are expecting in longitudinal strain. So Young's modulus Y, it's going to be normal stress upon longitudinal strain. So stress is what? Force upon area. Alright, this is stress. And what about strain? Strain is change in length upon original length. I am telling about the longitudinal strain. Now Young's modulus, that is going to be F upon A into change in length, that is delta L into L. Okay, so this is how we can find out the value of Young's modulus if change in length, actual length, force as well as area is given, and if Young's modulus is given, force is given, area is given as well as initial length is given, then we calculate the change in length delta L as F into L upon A into Y. Okay, just rearranging this. So basically you need to understand stress by strain. Okay, stress is F by A and strain is delta L by L. You will get the relation. Okay, so as I told you earlier, modulus of elasticity, it is supposed to have the same unit as that of stress, as well as the dimensional formula is going to be same as that of stress only. So here again you can see the dimensional formula is ml raised to minus 1 t raised to minus, the unit is Newton per meter square, or you can say Pascal. Next is force constant. Here this particular case, it has got no direct relation with the modulus of elasticity, but it is important to tell about the force constant here. So to understand that, I am going to consider a wire and I am going to attach a mass over here. So the mass is of m kg, so definitely the weight is going to be what? M into g. So if delta L is the elongation that happened for a wire of initial length L, okay, due to this weight of mg, the elongation happened here is how much? Delta L. Okay, now the force constant, which what it says is, we all know that F into L upon A into delta L is equal to what? Y. Okay, now let the elongation happen here be 1 meter. The elongation happened here is going to be what? 1 meter. Now I can say that F into L upon A, that's equal to what? Y. If I consider delta L as what? 1, then I can say that F into L upon A is equal to what? Y. Okay, now what is the force what we applied here then? The force applied here is A into Y upon L. A into Y upon L is the force applied. So basically the force that we need to apply onto any wire to create an elongation of unit length, that force is called as what? Force constant. And here the force constant is represented as K equals A y upon L. You can see the same relation here. Is that okay? Fine. Moving to the next, that is bulk modulus of elasticity. What was Young's modulus? That was normal stress upon longitudinal strain. Here it is going to be volumetric stress upon volumetric strain. Volumetric stress, what is volumetric stress that we know? And volumetric stress is what? Change in volume upon original volume. So you can see the relation here. K is equal to volumetric stress upon volumetric strain, and in case of Young's modulus we expressed it as F into L upon A into delta L, isn't it? In case of Young's modulus we explain like this, and here in case of bulk modulus it's going to be represented in terms of K only, capital K, there the relation is going to be F upon A. That particular relation is going to be the same. Instead of delta L, it's going to be delta V, and here this is going to be 1V. And we all know that F by A, that is pressure. So the same can be represented as P into V upon delta V. So that is what this relation you can see here. And definitely there is a minus sign here. Okay, why this minus sign? If there is an external force acting the inward direction, definitely the volume of the body is going to what? Decrease. Just to represent that only, we are having that negative sign over there. Okay, the next one is compressibility. Okay, fine. Compressibility is the reciprocal of bulk modulus. It's very important terms. It is reciprocal of what? Bulk modulus. I told you, related to the match the following, assertion, reason and all, these informations are very important. So what is compressibility? Reciprocal of bulk modulus. Fine. SI unit is definitely going to be the inverse of pressure. What was unit of pressure? It was Newton per meter square. The inverse of this is going to be what? N raised to minus 1 meter square. So the unit of compressibility is Newton raised to minus 1 m square. Alright. Next one is modulus of rigidity, which is also known as shear modulus. Terms are, I repeat again and again, terminologies are very important. Modulus of rigidity or shear modulus. Here this is going to be tangential stress upon shear strain. Tangential stress upon shear strain. And do you remember what was shear strain? It was that angular displacement, isn't it? So here modulus of rigidity eta, it's going to be F upon A, that is the tangential stress upon the strain. It can be taken as what? D theta or theta. Was that okay? Fine. Now next one is factors affecting modulus of elasticity. Questions were there. Okay, not so far in 2023 or 2022 the questions were there from this particular section. So ever never skip this area. Factors affecting what? Elasticity. Alright, the first one is see, the modulus of elasticity of the material decreases. Please note, it is decreases with increase in temperature. Okay, so if the temperature goes up, what will happen to the modulus of elasticity? Okay, it will be decreasing, except inward. Fine. Another one, annealing, due to annealing act. Okay, what will happen? Elasticity of the material decreases. Okay, fine. Next one is by hammering or rolling. By hammering or rolling, what will happen? Elasticity will increase. Okay, so here it was decreasing. Second case also it was what? I mean, first case it was decreasing, second case it was decreasing, and to increase the elasticity, what was the possibility? Hammering or rolling. Okay, now adding impurities. There the case is, it depends what type of impurities we are adding. Okay, now if the impurities adding is having elastic properties, so definitely it will go up. Okay, and if the impurities what we are adding is having less elastic property, it will come down. Okay, now for liquids the modulus of rigidity is what? 0, because it cannot withstand shear force. And another important point is Young's modulus Y and rigidity modulus eta. Okay, these are possessed by solid materials only. Okay, that means liquid as well as gaseous material, these two modulus we can't we can't define this modulus of rigidity or modulus of Young's modulus for solids, I mean gaseous material or liquid material. Okay, fine. So modulus of rigidity is 0 for what? Liquids, because it cannot withstand shear force. That is also an important point. So, here factors affecting elasticity, that was something very, very important. Okay, and temperature change, that was the question I told you. There were questions from the previous years. So, it was about the temperature variation. So, what happened to the temperature, like what happened to the elasticity when temperature was increased? Once temperature was increased, elasticity was what? Decreased, and annealing impact, again the elasticity was what? Decreased. Now, hammering as well as rolling, elastic property got increased. So, you can you can keep in mind like this. If you need to increase the elasticity, the possibility is what? Hammering. Okay, in other cases what will happen? It will decrease. And while considering the possibilities of adding an impurity, then definitely if you want to enhance the elasticity, the impurities that what we are adding, it must be having a greater elastic property. And if you want to decrease, so definitely the impurity that we are adding will be having lesser value of elastic property. Alright. Now, once I move to the next is Poisson's ratio. Alright. So, whenever we are stretching any wire, say like this, once we are stretching a wire like this, okay, let this be the initial length. So, once we stretch to a greater value of length, so definitely this cross sectional area will become what? Smaller. Okay. So, if there is a longitudinal strain, okay, that means fractional change in length, there is a lateral strain also. If there was a longitudinal strain, there is going to be what? Lateral strain. And what is lateral strain here? Change in radius upon actual radius, that is lateral strain. Now, that ratio of lateral strain upon longitudinal strain, I repeat, ratio of lateral strain upon longitudinal strain, that is what we call it as what? Poisson's ratio, and we represent it by letter sigma. Okay. Now regarding Poisson's ratio and its values, theoretically it's having value ranging from -1 to 0.5. Practically it's having value ranging from 0 to 0.5. Okay. And comes the relation between Y, that is Young's modulus, K, that is bulk modulus, then eta, that is shear modulus, and sigma, Poisson's ratio. Okay, the relation between all these four modus of elasticity term. So, basically we have got four standard relation, but I recommend you to focus on these two. Okay. The first one is Young's modulus Y, that is equal to 2 times eta into 1 plus sigma. Young's modulus Y is equal to 2 times eta plus 1 times sigma. And here Young's modulus Y, that is equal to 3 times K into 1 minus of 2 times sigma. That was 1 plus sigma, here it is 1 minus 2 sigma. There was 2 times eta, here this is 3 times bulk modulus. Are you getting me? Now, rearranging these two formulas will give equation number 3 as well as equation number 4. There were again previous year questions based on this. Okay, so don't skip this part. Okay, I recommend you to understand these two relations. There it is, Y is equal to 2 times eta plus 1 plus sigma. Okay, and here it is 3 times K into 1 minus of 2 times sigma. On both the sides it is Y, so it is better to correlate these two relations. Alright, next is some important points. Alright, these two area, again it was there in PY. Okay, so the points are, for same material, coefficient of elasticity, that is Y, eta and K, can have different magnitudes for same material. okay, because why? It's telling about longitudinal stress, I mean normal stress upon longitudinal strain. K, it was telling about, it was dealing with what? Volumetric strain, fine, and eta was telling about what? Its shearing capability. So definitely the deformations happening is different, so obviously this elastic modulus, I mean modulus of elasticity is going to be different for same material. Okay, so that's point number 1. Same material can have different value of y, eta as well as k. Point number 1. Next one is for isothermal elasticity of gas. Okay, that then is there the volumetric changes are possible. It cannot withstand shear stress, and it cannot withstand tensile force or compressive force and all, isn't it? Like elongation, linear elongation is not, but compressibility is there, okay, for the gas. So isothermal elasticity for gas, that is E suffix T, is going to be what? P. Okay, so modulus of elasticity at constant temperature, that is the point. Modulus of elasticity at constant temperature for a given gas, it's going to be what? Pressure at that given moment. What is the pressure? That's going to be the modulus of elasticity. Okay, next one is modulus of elasticity. Okay, if the process happening is an adiabatic, that means there is no heat exchange taking place, then E suffix S, that means modulus of elasticity, that is going to be gamma times P, again P is pressure at the given moment. What is gamma? Cp by Cv. Alright, so Cp by Cv, which is equal to gamma, that can also be explained in terms of modulus of elasticity. And what's that ratio is going to be? It is Es by Et. Alright, fine, because I told you what was this? This is Et, isn't it? So Es upon Et, that's what? Gamma, and that is Cp by C. So you can see that relation here. Okay, I told you these 2 points were there, so definitely I thought I must consider the other terminologies also. That's why this slide is here for you. Okay, and now let me take you to the next, that is breaking stress. So let me consider a wire onto which I am continuously applying a force, and as a result of that elongation is happening. Okay, and definitely beyond a particular point, we cannot keep on adding the force, isn't it? So there is going to be a maximum value of force definitely, okay, beyond which if I add, or if I increase the load or apply a force, the wire will break. So the maximum force upon area, that is known as what? Breaking stress. Okay, so once we know the breaking stress, that means definitely there is going to be a safety factor. Now breaking stress, that means the maximum value of force that can be applied perpendicular to the that particular surface per unit area, that is what? Breaking stress. And breaking stress upon working stress. Working stress means actually what is the load being experienced by a given wire or a given structure, and breaking stress is the maximum possible. How the safety factor is important here is, let us consider a case where working stress is very less than the breaking stress. Okay, so definitely the safety factor is going to be a value of comparatively a bigger value it's going to be, because working stress is very less and breaking stress is very high. Okay, and so there the structure is safe. Okay, there the structure is safe. And if the breaking stress and working stress both are the same, then the safety factor is 1. Okay, the safety factor is 1. That is a dangerous situation. Anything may happen. Okay, that's a critical situation. And if it is less than 1, it's over. Definitely the structure will collapse because it cannot withstand that force, isn't it? So there, that bears the importance of that safety factor ratio. Next one is elastic relaxation time. elastic relaxation time. So, whenever we are applying a force and the deforming force is removed, it's not like that you remove the force and all of a sudden the body get back to its original shape. No. Definitely there will be a time gap. It need a time for the deforming force will be acting and taking the body back to its original shape. So, obviously that time lag is known as what? Relaxation time. The next one is elastic after effect. The name itself, it's there, it's after effect. Okay, so basically the temporary delay, here it was the time taken and the temporary delay of any given material to get back to its original shape, that is known as what? Elastic after effect. And the last one is elastic fatigue. If you apply a force on a particular material, obviously deformation is going to happen, and if loading, unloading happens for a long duration of time, fine, definitely the elastic property of the material is going to be lost, okay, and that will be reduced, and that we call it as what? Elastic fatigue. Okay, the next one is ductile material, brittle material, elastomers. Okay, again match the following area, we can expect questions related to this one. Okay, first one is, what is ductile material? Okay, here it shows a large plastic range beyond elastic limit. That means if you apply a force beyond the elastic limit, okay, this shows what? A large plastic range. That means there is a possibility, that means the possibilities of deformation of this particular object, this particular material is very large. Okay, the second one, now there itself we need to, we can discuss about what? Few examples. We all know that the wire what we use at our home, isn't it? So it's like that linear structure, you know that it's made of what? Copper, and that copper is pulled into a wire shape, isn't it? So how it happened? That's not, naturally that the copper is not available in that form. Definitely we extract that, isn't it? Now we get it as a bigger structure. Now we are stretching it into thin wire of the dimension that what we need. Okay, that means pull into the shape of a wire. That is possible because of what? Because the elastic property is lost for that material, and now we are stretching it, and what? Finally we are getting into the form of a wire. So that particular materials hold a property known as what? Ductility, and such type of material is known as what? Ductile material. The next one is brittle. Brittle can directly connect that word to the name bottle. Okay, glass bottle. If you give a very slight possible deforming force also, what? You cannot pull a glass into form of a wire, or you cannot twist any glass bottle into another form, isn't it? Whenever a deforming force is applied, what will happen? It will break. So that particular that type of materials is known as what? Brittle material. And the next one is elastomers. Elastomers. What are elastomers? In this case, the strain produced is much larger than the stress applied. For example, you can say rubber. Okay, they are what? Elastomers. Alright, and the next one is malleability. Okay, so here what happens, in case of that ductile, we can pull it in form of a wire. That is ductility. And malleability is, it can be compressed into form of a sheet like structure. That particular property is what? Malleability. Alright, the next one is elastic hysteresis. Elastic hysteresis is nothing. Once we keep on applying a load, okay, and loading and unloading, then what happens? The elastic property will be lost, and we define that as what? Fatigue. And here what happens is, in this way, if you keep on doing so, the storing and loading and unloading, it will keep on dissipating the energy. Okay, and as a result of that, this particular material is going to lose that property forever, and that we call it as what? Elastic hysteresis. Alright, so then what happens is, later on, if the load is applied like this, for example in this way, okay, here this is stress and here this is strain. And if loading and uploading, I mean loading and unloading, it happens initially, the way it go up, that means while loading is being done, stress will keep on increasing, and once it is removed, it need to come back in the original way. But if you keep on doing for a long duration of time, it won't be coming exactly in the actual path. Okay, so that particular phenomenon is known as what? Elastic hysteresis. And moving to the next, that is elastic potential energy. Here, let us consider a case where I am having a wire of length L. Now, I am applying a force of F here. Okay, as a result of that, let me consider a change in length, that is delta L. Okay, now the force applied capital F, the change in length what happened here is delta L, okay, divided by 2. That is called as the potential energy. So basically, we can define it as what? Average force upon increase in length. F into delta L divided by 2, that is the elastic potential energy. Okay, now multiplying with capital L and dividing by capital L, the same equations can be modified as half of stress into strain multiplied by volume of wire. Okay, you need to just multiply it with capital L and divide by capital L, again multiply by capital A and divide by capital A. So F by A is going to be strain and L into A is going to be what? Volume. So there you will get it as half of stress into strain multiplied by volume. So, and if I again divide this by volume, that is energy stored per unit volume, then it is going to be what? Half of stress into strain. Alright, fine. So basically the standard expression is going to be this. Alright, from here you can get into any of this format like this one. I repeat, the energy stored is going to be half of F into delta L. Okay, now what you need to do is multiply it with L and divide by L, multiply it with A and divide with A. There it will take you to the all this format. It's as simple as that. Alright, the next one is thermal stress. Here what happens, you know, whenever you increase the temperature of any particular substance. Okay, let this be a given material. Alright, so whenever I increase the temperature, most of the case what happens, there will be a thermal expansion. And what you need to understand is, what if I am keeping this particular material between the walls like this. Okay, so once I increase the temperature, it is having a tendency to expand. Okay, so if this wall was not there, definitely it should have expanded to a length like this. But actually a wall is here. So I can assume that an expansion happened and this wall compressed this particular material back to its original length. Okay, in that case definitely what is there? A stress is developed. Alright, such type of stress is known as what? Thermal stress. Okay, so the thermal stress is defined as again Young's modulus Y into coefficient of thermal expansion alpha multiplied by delta theta, where delta theta is the change in temperature. Alright, fine. So that was about thermal stress. So now let's move to the next topic, that is properties of fluids. Okay, so here for this particular chapter we will be addressing this in two categories. First one is hydrostatics and second one is hydrodynamics. Okay, so the first one is hydrostatics. Alright, so here we will be defining what is fluid, and next one is about the stress generated due to the fluid. Alright, and of course what we discussed, what is hydrostatics and what is hydrodynamics. That is all here for the first page. So what is fluids? Okay, fluid is anything that can flow. Okay, so anything that can flow is known as what? Fluid. And there liquid as well as gas both falls under the category of fluids. Alright, now why this particular fluid can flow is just because of one reason: it cannot withstand shear force. or you can say it cannot withstand shear stress. That is the reason why gas as well as liquid can flow and solid cannot flow. Okay. Now, whenever we do make study regarding fluid, the way that a fluid which is not flowing as well as the way which a fluid is kept inside a container, it behave, there is a difference. That is why we are having two different branch of study for that. First one is hydrostatics and second one is hydrodynamics. So while considering the study of fluid which is at state of rest, of course that is going to be kept in a container. So whichever the container in which that particular fluid is kept, so the shape of that fluid is going to be exactly same as that of the container in which it is kept. Especially for the case of liquid, the shape is going to be like that. And for gas, what happens is that fills the entire space of the container, you can say. So you must understand, if this is a container and if there is a liquid like this, so up to this particular level it's going to occupy a shape like this, and definitely if the shape got changed like this, okay, and the same volume is transferred, the shape can be changed in this way. And if this is a closed container and instead of a liquid, if it is a if it is a gas, then it's going to completely fill the space. Okay, that also must be kept in mind. Okay, now next one is thrust as well as pressure exerted by a fluid. Okay, basically we know what is thrust. Thrust is the normal force acting. It is the normal force exerted by the fluid, and that normal force divided by area, that is we call it as what? Pressure. Unit as well as the dimensional formula is going to be same as that of pressure only. And for thrust, since it is the normal force acting, it's going to have the same unit as that of force, as well as dimension is also going to be same as that of the force. Was that okay? Now let me take you to the next, that is pressure exerted by a liquid column. This topic is very important. Now for easy understanding, let me consider a container like this, and let this be filled up to a height of say h. Okay, so here the height is h and the density of the liquid is rho. Acceleration due to gravity is g. Okay, and here since atmosphere, the presence of atmosphere we are considering, let me consider the pressure due to the atmosphere be P0, or you can say atmospheric pressure is P0. Now if I consider any point at a depth of say h dash, here it is marked as h I believe, so I need a correction here. I need to mark this as capital H and I need to mark this as small letter h. Now for any point which is at a depth of h, let me name it as capital A, then pressure at A is going to be atmospheric pressure P0, atmospheric pressure P0 plus rho into G into H. Okay, that is going to be the pressure due to a liquid column. Clear? P0 is atmospheric pressure. In addition to that, the pressure due to the liquid column, that is rho G H. Clear? Now, how the variation of pressure is taking place with respect to the depth. So, for understanding, I know I am left with some space over here. Now, let this be a point here, that is A. Now, here this is point B. Now, you can see this is of height small letter h. So, definitely the pressure at this particular point is going to be PA, and I am marking the pressure here as what? P suffix B. Okay. Now, let me take this height as x. I am going to take it as what? X. Now, tell me what is PA? So, definitely PA is going to be P0, that is atmospheric pressure, plus rho into G into X. What about PB? PB is going to be P0, it's going to be P0 plus rho G into X plus H. Okay, now if I want to take the pressure difference, like of course PB is greater than PA, so I can say PB minus PA is going to be this one minus this. Again that is going to be what? Rho into G into H only. Okay, and one more thing, that is, again let me consider a liquid column like this, and the height of the liquid column is what? H. Okay, now definitely you know that here the pressure is lesser, and once we move in the downward direction, the pressure acting due to the liquid column is what? Keep on increasing. Okay, so because the height is, while moving in the downward direction, H value is increasing, and as a result of that the pressure also will be increasing. So if I want to calculate the average pressure, I repeat, the average pressure experienced by the walls of the container, that is going to be rho into G into H by 2. So that is going to be the average pressure experienced by the wall of the container. Was that okay? Now let us move to the next topic, that is atmospheric pressure. So here, while telling about the pressure experienced because of the liquid column at any particular point, again and again I was telling about the atmospheric pressure, the presence of atmospheric pressure. In this case atmospheric pressure P0 was taken as what? 0 only. That's why I wrote it as what? Rho G H by 2. Okay, and in this case as well as here also I spotted the presence of atmospheric pressure. So here in this slide we are going to tell what is that atmospheric pressure. So definitely, as the name indicates, what is atmospheric pressure? Normal force per unit area due to the atmosphere. That is known as what? Atmospheric pressure. So one atmospheric pressure in SI system, it is 101,325 Pascal, which can also be written as 1.013 into 10 to power 5 Newton per meter square, and the same value it is marked as what? 1 atmospheric pressure also. Now again atmospheric pressure, here this was 1 atmospheric pressure, and I told you that is 101,325 Newton per meter square, and this is again mentioned in terms of height of mercury column, that is 76 centimeter of mercury. Okay, so how we convert this 76 centimeter of mercury into a pressure value? Basically using the relation P is equal to rho GH. Okay, so the concept is the pressure exerted due to 76 centimeter long mercury column. Okay, fine, that is 1 atmospheric pressure, and there you must understand one thing, what is the density of mercury? That is going to be 13.6 into 10 to power 3 kilogram per meter cube, and of course in CGS system you can take acceleration due to gravity G as 9.8. That is how we calculate the atmospheric pressure. Directly we can get this one, and in terms of mercury it is, I told you, it is 76 centimeter of mercury, and there again I repeat, you must not miss the density value of mercury, that is 13.6 into 10 to power 3 kilogram per meter cube. Okay, now other than this we have got 2 more units, that is torr and bar. One torr, that is 1 millimeter of mercury column. One torr is 1 millimeter of mercury column, and one bar is 10 to power 5 Pascal. Okay, so these unit conversions must be very clear. I repeat once again, one torr is 1 millimeter of mercury column and one bar is 10 to power 5 Pascal. And what is 1 atmospheric pressure? 1 atmospheric pressure is 101,325 Newton per meter square. Alright, now the next one is some important points related to fluid pressure. Okay, these concepts are very important. The first one is, at a point in the liquid column, the pressure applied is all the same in all the directions. It is same in all the directions. That means if I consider a liquid column like this, so let me consider a point here. So the pressure exerted in all the directions from this particular point is supposed to be what? The same only. That is point number 1 says. Alright. Now second point says the pressure will be same at all points in the same level. Which means if I consider a liquid column like this and I draw a horizontal line. Let me take point A, let me take another point B, and let me take another point C. So here pressure at A is going to be same as that of pressure at B, is going to be same as that of what? Pressure at point C. That is the second point. Now the third one is the pressure exerted due to the liquid column is independent of the shape, and that only depends on the height of the fluid. What it means is, let me consider a liquid column like this. Let me consider another liquid column like this. And let me consider another liquid column in this way. Okay. Now, let me connect this particular system in this manner. Alright. So, here you can see the liquid is up to same height. Fine. Now, here on a horizontal line, I need to mark this as A, and I am marking this as B, and I am marking this as C. Now here above point A I am having a narrow tube, above B I am having a tube, again a tube, a shape of similar to that of a tube, but it is occupying a greater volume, and here it is a bottle like structure, not at all comparable with the shape number 1 or column number 1 or column number 2. But though there is a shape difference in all the three cases, one similarity you can notice: point A, B as well as C, it is at same depth from the surface of the liquid. So here pressure at A is going to be same as that of pressure at B, is going to be same as that of what? Pressure at C. That was the 3 points that explained here. Okay. Now we are moving to the next slide, that is regarding the shape only that we already discussed. They have given some another diagrams, that's all. Okay, so the pressure is going to be same if the height is the same thing, that's all. Okay, so definitely here if atmospheric pressure is there like P0, if it is marked, okay, so here you can see P0 atmospheric pressure is marked. So irrespective of the shape, it's going to be same at all the points. What is going to be the pressure then? It's going to be P0 plus rho g into h, where h is the height of the liquid column. Is that okay? Now we are going to the next, that is what is going to be the pressure in this case. Okay, so here what you can see is I am having a liquid column, okay, and there I am having a block of mass m. Okay, now atmospheric pressure is here, that is what? P0, and I am going to consider a point here. Let me mark it as A. Okay, now this cross sectional area, it is capital A, and let me mark this point as say small letter A. Now pressure at small letter A, I am going to mark it as capital P. Okay, that's going to be definitely atmospheric pressure P0 plus definitely the pressure due to the liquid column, that is rho into G into H, plus definitely the weight of that block is also going to be there, that is M into G, and once I want to consider the pressure due to that weight, it's going to be mg by A. So here this is going to be the pressure at any particular point if I am having a block of mass m partially or fully immersed like this. Okay. Now the next one is buoyancy. So here you can see this particular block was dipped inside the liquid. Fine. So once it is dipped inside the liquid, you know that the pressure force is supposed to be experienced by this block, isn't it? And you know that is supposed to act like this normally in all the directions. So now this particular body which was inside the liquid, it is experiencing a normal force because of the liquid, okay, and that normal force, if we consider that normal force, you know, let this be the block. Now here the force is lesser, here it is greater, here this is greater, here this is lesser, here this is greater, and here this is greater. So of course you know that there is an unbalanced upward force, alright, and we are telling about that unbalanced force here. Okay, so once a block is partially or fully immersed like this, this is going to experience a net upward force, and that upward force is known as what? Buoyancy. Clear? And that the phenomenon is known as buoyancy, and the force is called as what? Buoyant force. It is known as what? Buoyant force. So there is a net upward force, and we call it as what? Buoyant force, represented by F suffix B generally. Okay, and the next one is Pascal's law. Okay, what Pascal's law says is, let us again consider a liquid column like this. Here the pressure is P0, and at a particular depth it's going to be P equal to P0 plus rho GH. Now by any means, if I increase the pressure to 2 times P0, okay, now this increase in pressure, I repeat, this increase in pressure, it is going to be equally transmitted in all directions. What I mean to say is, if I have got an arrangement like this, liquid column is here and so this liquid column is here. So if definitely atmospheric pressure is going to be P0, so here also it is supposed to be what? P0 in normal case. So by any means, say by the help of a piston, if an additional pressure of 2 times P0 is applied, so altogether the pressure at this particular point is going to be what? P0 plus 2 times P0, that is going to be 3 times P0. So there is a pressure difference of delta 2 times P0 was generated. So if I consider a piston here, so that piston is also going to experience the same pressure difference, that is delta P is going to be what? 2 times P0. So I applied the pressure here, but it got transmitted to the other end. So that is what I mean to say, if a change in pressure is there, okay, then that change will reflect in all directions. That is what Pascal's law says. Next one is Archimedes' principle. Alright, so what Archimedes' principle says that when we have an arrangement like this, okay, so this particular block, let W be its weight in air, W be the weight in air, okay. Now if this particular arrangement is taken to a setup like this, okay, and let me now weigh the same arrangement using a weighing balance, like let this be a spring balance, this manner. So here it's immersed in the liquid, isn't it? Right? It can be fully or partially immersed. Now here this is going to be W dash, or you can say W inside the liquid, W inside the liquid, okay. Now of course, since there is a buoyant force in the upward direction, I repeat, since there is a buoyant force in the upward direction, W dash is going to be what? W dash is going to be W in air, okay, minus of what? F suffix B, buoyant force. Because the net pulling force, that's going to be measured by the spring, isn't it? So W dash is going to be what? W in air minus of F suffix B. Now I can see there is a loss of weight. And what is that loss of weight? actual weight is marked as W air minus W dash, or you can say W in liquid. This is the loss of weight, delta W. And what is that delta W? Delta W is going to be what? The buoyant force, F suffix B. Okay, so what I mean to say is that when a body is partially or fully immersed inside a liquid, that will be experiencing a weight loss, and that weight loss is going to be what? The buoyant force. Okay, that's going to be the buoyant force. And here I want to tell you something very important. So here you can see so many relations are here. All right, fine. So I am going to tell you how to connect with all these relations. Okay, so for your reference you can go through all these relations. So here like I will explain this one by one. Before that, I would like to tell you how you can connect to all these relations initially. All right, so let me consider another slide for this. Let me consider again a column like this, a mass, okay, and let this particular density of the liquid be rho of liquid and density of this particular material be rho. Okay, now consider a situation where this particular body is completely immersed like this. Okay, this is the easiest method to understand. It's completely immersed like this. That means the weight of the body, and here we are ignoring the atmospheric pressure. Okay, for easy understanding, we are ignoring the atmospheric pressure. Now here, if I understand this particular situation, the weight of the body is completely balanced by what? The buoyant force. So the weight of the body is going to be rho, that is the density of this material, and capital V is the volume, okay, of this particular body, into G is acceleration due to gravity, and that is now equal to, now the weight, the buoyant force is supposed to be, I repeat, buoyant force is supposed to be volume displaced multiplied by density of the liquid multiplied by acceleration due to gravity. This is the buoyant force. Okay, now here this is rho of liquid into, here this is completely inside now, so we will be going for volume as capital B only, multiplied by acceleration due to gravity G. So G and G will cancel each other. Okay, and V and V will cancel each other. So here I can say rho is equal to what? Rho of liquid. That means the density of the liquid as well as the density of the solid material that we consider over here, if it is same, then it will be what? It will be just floating like this. Okay, now go back to this. Total volume is capital V and volume inside is V dash. Total volume is capital V and volume inside is what? V dash. So if that is the situation, again weight of the body is V into rho into G. That is equal to volume of the liquid displaced is V dash, rho of liquid is the density of the liquid, and G is acceleration due to gravity. Again G and G will cancel each other. Now you can see one important relation here. See, V dash upon V, that means the volume of the body which is inside the liquid upon actual volume, V dash upon V, that is going to be what? That is going to be density of the liquid, V dash upon V, V dash upon V, V dash is here now, so V dash upon V is going to be density of the material upon what? Density of the liquid. Are you getting me? Fine. So here I repeat once again, capital V was the actual volume. So what fraction of volume is inside? What fraction of volume is inside? If you want to find out that, volume inside the liquid, that is V dash upon actual volume, that is equal to, okay, density of the material upon density of the liquid. This is that relation. Okay, which means see, here this density of the material is greater. So once the density is greater, the volume inside will what? Keep on decreasing. So if I increase the density of this particular liquid, it was a raw liquid, isn't it? So if I increase, then what will happen? The volume will what? Decrease. Volume inside the liquid will decrease. So what happens is, if I increase this particular value, if I increase this particular value, that means in the denominator, what will happen? This exact value will come down. So if this exact value need to go down, definitely what must happen? Definitely V dash must go down. Are you getting that point? So that particular part is very, very, very important. So volume inside upon total volume is density of the material upon density of the liquid. This is the most important relation that throw light onto these relations. Okay, and here also, this particular relation, what it was telling about? Here it was telling about the weight loss. Alright, here this was telling about the weight loss. And what was weight loss? Definitely the weight loss was equal to buoyant force experienced by that particular body which is partially or fully immersed inside the liquid. Okay, now comes this relation. First of all, let's have a look. We are having two cases. Okay, case number 1 is that is marked as A. Okay, and case number 2 is marked as B. Fine. So here what happens is, here I am having a body which is weighed in air. I repeat, weighed in air, and second case it is weighed in a particular liquid. Okay, then there is going to be a weight loss. So weight loss in air, weight in air minus weight loss in the liquid. Okay, that means the weight in the liquid, that's going to be the weight loss. I repeat, weight in air minus weight in the liquid, that is going to be the weight loss. Weight loss. Okay, and here this is weight loss in liquid. Fine. And the next one is weight in air, and here this is weight in water. So here this is weight loss in the case of what? The water. Okay, now have a look. When a body is partially or fully immersed in a liquid, it loses some of the weight and it is equal to weight of the liquid displaced by the immersed part of the body. So if A is loss of weight, and next one, if B is loss of weight in another liquid, then W actual weight, okay, minus weight of the liquid that displaced, that's going to be the weight loss. So you may mark it as what? A by B. I already told you exactly this is that relation telling about, isn't it? I told you about that weight loss condition here. So that is taken for two separate liquids here. That means one is liquid and another one is what? Water. Now have a look. Here density of the body is given as what? Rho. Okay, now it is partially immersed inside the liquid. Then the actual weight of the body is what? Actual weight of the body is W. Okay, now T is what? The apparent weight. T is what? Apparent weight. In that case, actual weight W, that is going to be apparent weight T into 1 minus of rho by sigma. What is rho here? Rho is the density of the liquid. Rho is the density of the liquid, and sigma is what? The density of the material that we have considered here. Okay, so here it's T is marked as what? The apparent weight, and W is marked as what? The actual weight. Okay, now have a look. Here I told you about the actual weight as well as apparent weight, isn't it? Fine. What was the apparent weight here? In this case, if this was the condition, what should have been the apparent weight? Apparent weight should have been actual weight minus the weight of the liquid displaced. And what is the weight of the liquid displaced? Weight of the liquid displaced is going to be the volume of the liquid displaced, that is V dash. Okay, here rho liquid was the density and G is going to be what? The acceleration due to gravity. So here this is actual weight, and here this is the weight loss, and here this is going to be the apparent weight. What? Apparent weight. And here as per this particular relation it is marked as capital T. So I am considering the same thing here as well. Okay, now W minus of, we have got a relation for V dash. What is V dash? V dash is V into density of the material, isn't it? Density of the material is marked as what? Sigma here in this case. Okay, density of the material is marked as what? Sigma in this case. Alright, now So here I am taking it as density of the material upon density of the liquid. Density of the material is, density of the liquid is taken as what? Rho here, alright, into rho into G, that is the apparent weight T here. Okay, now have a look, rho and rho will cancel each other, rho and rho will cancel each other, isn't it? And what we have got? Capital W over here, and V, what is V? That is the volume of this particular material, isn't it? Now volume of the material, we all know that mass by volume, that's equal to density. Mass by volume equal to density. So volume is going to be what? Volume is going to be mass by density. So that will appear here. So W minus of, instead of V, I am going to write as what? M upon rho. Okay, into sigma into G, that's going to be what? T. Now M into G is what? Again W only. Alright. So if I rearrange this, I can say that W is common, 1 minus of, okay, 1 minus of what I have got here. What I have got is sigma divided by G, that's equal to what? T. This is that relation. You can see it here. Alright. So that was that particular relation. It is very important, isn't it? Alright. So you can see W is equal to T divided by 1 minus of rho minus of sigma. The same thing is arranged like this. Okay. So I explain what is that standard relation. What was that standard relation? Standard relation was this. And from that standard relation, whatever the situations are given, in that way you can arrange the cases. Okay. One more case I want to tell you, that is, let me consider a case like this. Okay, like this is liquid number 1 and this is liquid number 2. Let me have a case like this. So here this is rho 1 liquid and here this is rho 2, and let this be what? Rho. Density be like this. Okay, fine. Now for this given situation, I can say the actual weight of the body is going to be volume of the body, that is rho, V into density is rho multiplied by acceleration due to gravity, G. That's actual weight. Now that is now equal to this much volume of liquid is displaced from liquid number 1. So I can say it's going to be what? V1 into rho 1 into G. That means that out of capital V, V1 volume is there in liquid number 1 and V2 volume is in liquid number 2. Okay, so V1 volume into density, that is mass, M into G, that is the weight. Okay, so V into rho into G, that is equal to V1 into rho 1 into G plus here V2 into rho 2 into G. So here G and G will cancel each other. So what this now going to be? V into rho, that's going to be V1 into rho 1 plus V2 into rho 2. Now one more thing, we know that V1 plus V2 is equal to what? V. Alright. Now there might be cases where they are asking for the ratio of V1 by V2, okay, or what fraction of volume, V1 by V, or it could be a V2 by V1, in any way they can ask. Alright, so this particular relations, these two relations, that is V into rho is V1 rho 1 plus V2 rho 2, and V1 plus V2 is equal to V. These two equations will help you a lot, definitely. Will help you definitely a lot. Okay, especially related to these type of cases. Alright, now let's move to the next, that is law of flotation. So based on the buoyant force as well as the actual weight of the body, okay, how could a material behave inside the liquid? If W is taken as the weight of the body and F suffix B is taken as the buoyant force. If W is taken as the weight of the body and F suffix B is taken as the buoyant force, and case number 1, if W greater than F suffix B, the body will sink. W less than F suffix B, okay, W less than F suffix B, it will be partially immersed, and W is equal to F suffix B, it will be just floating. I repeat, if W is greater than F suffix B, then you can see a body here, it got sinked. and if F suffix B is less than W, it will be partially floating, and if F suffix B is equal to W, then this is what you are going to observe. Okay, so W greater than F suffix B, W less than F suffix B, okay, and here W is equal to F suffix B. Okay, now you must understand one thing. This F suffix B is that particular force once the body can completely be inside the liquid. So here, if this is in equilibrium as well as this is in equilibrium, so practically saying W is equal to F suffix B, that is why it is floating. And what I wrote it as W less than F suffix B means, if this particular body is completely inside the liquid, even then the buoyant force is F suffix B. Okay, then that F suffix B is compared with capital W here. So don't get confused. Okay, so here F suffix B will be generated only to cancel the value of W only, so it won't be completely immersed. Alright, and so definitely this particular part we already discussed, that is fraction of the body, fraction of the volume that is out of the liquid. In detail we had a discussion, same relation is here. There we discussed in terms of rho 1 and rho 2, okay, as well as in terms of rho and sigma also, the same thing you can see here as well. Now again in terms of some other relation like rho 1 in liquid A as well as rho 2 in liquid B, two type of comparison of liquid is taken. Alright, so what is going to be the volume inside the liquid of type A, and here this is volume inside once the liquid was B, that is going to be rho of A as well as rho of B based on the density they have telling about. Okay, and here it is about in terms of density of the body. So here you can see it's in reverse, volume inside is here, it is directly proportional, and here this is inversely proportional, so that must be in your mind. And the next one is density as well as relative density. Density you all know that's what, basically mass by volume, and relative density is density of a given substance upon density of water, that is also an important term. And next one is density of mixture of a liquid. Okay, that means we are having two liquids, that is of mass M1 as well as M2 separately kept, and M1 liquid is having a density as rho 1 as well as M2 liquid is having a density as rho 2. Now the density of the mixture, that's going to be rho equals rho 1 rho 2, okay, into M1 plus M2 all divided by M1 rho 2 plus M2 rho 1. This is going to be the relation. Okay, and how to get into that one is, if you ever forget, you can take it like this. Density, effective density is going to be like this. Effective density is total mass upon total volume. What is the total mass? Total mass is M1 plus M2. What is total volume? V1 plus V2. And what is V1? V1 is supposed to be, so here I am going to write as V1 plus V2 only. Okay, now we all know that mass by volume, that is what? Density. Alright, so volume V, that is supposed to be what? M by rho. So here density of the mixture is going to be M1 plus M2 all divided by, instead of V1 I can go for what? M1 upon rho 1 plus here this is going to be M2 divided by rho 2. If I rearrange this, this is going to be the final equation. It's as simple as that. Okay, now some special cases. Special case number 1. What if M1 equal to M2 equal to M? What if M1 equal to M2 equal to M? So definitely in this equation M1 plus M2 is going to be 2M, and here M will cancel out, M will come out, so M and M will cancel each other. So in that condition density is going to be 2 times rho 1 rho 2 all divided by rho 1 plus rho 2. This is that relation. Alright, and the next one is, what if the volume is same? What if the volume is same? If the volume is the same, it's going to be rho 1 plus rho 2 by 2 average density. Next one is how density varies with pressure. Okay, so if rho 1 is the initial pressure and rho 2 is the final pressure, then rho 1 by rho 2 is going to be 1 minus of delta P by K, where K is bulk modulus. And how it's going to vary with respect to the temperature, that's going to be rho, that is rho naught into 1 minus of gamma times delta T, where gamma is coefficient of volumetric expansion. I repeat, coefficient of volumetric expansion. Don't compare this with gamma Cp by Cv. This is coefficient, like coefficient of linear expansion, coefficient of superficial expansion, as well as coefficient of volume expansion is there. So this here gamma is coefficient of volume expansion only. Okay, and now next we are moving to hydrodynamics. So here the first point is about streamlined flow and laminar flow. So we must know what is streamlined flow first. Streamlined flow first. Okay. So whenever a liquid is flowing like this, okay, let this be a pipe. Okay, let this be a pipe, and this is the cross section, and the liquid is flowing in this manner. Now let me consider the movement of one particle. So here the particle is moving in this track. Okay, here it was position first, now this is the position, now this is the position, and now this is the position. Now if the velocity of particle at 1, okay, now particle 1 moved to position 2. Now the next particle which is following the very first one. So here if I consider the particle motion, this is the one which is leading. Now these all are the trailing particles, isn't it? Now all these trailing particles will be having the same velocity as that of the preceding. Okay, that type of flow is known as what? A streamlined flow. And if the same type of flow is happening over a surface, there we call it as what? Laminar flow. Okay, and now if I consider this path and join it using a smooth line, we call that as what? Streamlines. Okay, and always remember, two streamlines cannot cross each other. Okay, and one more point is that, point number 3, that says greater the crowding of the streamline, greater the crowding of the streamline, greater is going to be the speed or velocity of the liquid there. Okay, that means if you can see a flow like this, so here the crowding is greater and here the crowding is comparatively lesser for a given area. For a given area, like here you can see the relative spacing is lesser and here the relative spacing is greater. That is what we mean to say that crowding. So definitely speed will be greater here and speed will be lesser here. Alright. Now the flow which is not a streamlined flow, the flow which is not a streamlined flow, that is what we call it as what? Turbulent flow. Okay. Now the velocity value beyond which, the velocity of the flow of the liquid beyond which the flow of the liquid changes from streamlined flow to the turbulent flow, that is known as the critical speed or critical velocity. Alright. Now next is equation of continuity. Equation of continuity says, if we are having a case of a streamlined flow, here the cross sectional area be A1 and here the cross sectional area be A2. Here the speed by which the particle is moving is V1 and here the speed by which the particle is moving is what? V2. Now as per equation of continuity, A1 V1 should be equal to what? A2 V2, and that will be always a constant. Okay, and if I go for V versus A relation, it's going to be inversely proportional. Okay, now the next one is the energy of the liquid flow. Okay, while considering the liquid which is flowing, we are going to consider the energy in 3 parts. First one is pressure energy. Okay, second one is kinetic energy, and third one is potential energy. And pressure energy itself we will be explaining in terms of unit mass and we will be explaining in terms of what? Unit volume also. If we explain in terms of unit mass, it's going to be pressure P by rho, and if it is explained in terms of unit volume, then the pressure energy is going to be capital P only, where P stands for the pressure. And while telling about the kinetic energy per unit mass is going to be half of rho into V square, and energy per unit volume is going to be half of rho into V square. Potential energy per unit mass is going to be G into H, and potential energy per unit volume, that's going to be rho GH. Okay, fine. Next is Bernoulli's theorem. Bernoulli's theorem says energy per unit volume, okay, that is pressure energy per unit volume plus kinetic energy per unit volume plus potential energy per unit volume is always a constant, and this particular relation is known as what? Bernoulli's theorem. And you can see different variant of that one, that is nothing, we just divided that with rho into G, so you can see another form of what? Bernoulli's theorem. And here P upon rho into G, this is known as pressure head. Now V square upon 2G, that's known as velocity head, and definitely H is what? Gravitational head or potential head. Alright. Next one is some applications of Bernoulli's theorem, okay, like the paint gun, then carburetor, sense spares. Alright, all these are what? Working, that all designs are made based on what? Bernoulli's principle only. Now another thing is motion of spinning ball, which is also known as what? Magnus effect. I told you in the beginning itself, match the following type of questions, then assertion reason type of questions, and everywhere these type of informations will be very helpful. Okay, now the blowing of roof because of the wind, then fluttering of the flags, okay, these all are what? Different applications. So you yourself can go through the application of Bernoulli's theorem. So whatever like came into my mind, all of a sudden I marked it over here. Alright, the next one is one more thing, airplane. Okay, why the airplane is able to fly in air, that is again based on what? Bernoulli's theorem only. Okay, next one is Venturi meter. Alright, so basically Venturi meter is designed to help us to measure the rate of flow. Alright, so here I can tell you what it stands for. Let a flow of liquid be taking place through a pipe like this. Here the cross sectional area is A1, and here the cross sectional area is what? A2. Here the speed of the liquid, it is V1, and here it is what? V2, and here I am having a tube like structure which is open to the atmosphere. Now you can see here the liquid is up to a particular height, say H1, and here it is up to a height of what? H2. Now between these two levels there is a difference, that is smollett H. Okay, so if that is the condition, then V, okay, the rate of flow, the rate at which the liquid is flowing, that is dV by dt, that is going to be rate of flow, that's going to be what? A1 into A2 under root of 2 times G into H upon A1 square minus A2 square. That's going to be the relation. Okay, so what is A1 and what is A2, that I already told you. Fine. So we just need to know about what? The liquid, area of cross section of the two area as well as the height variation in the liquid column. Alright. Next one is Torsell's theorem. So what it says is, we are having a container like this, which is holding liquid up to a height of capital H. Now from the surface at a depth of smollett H, we are having a small opening and the liquid is falling out like this. Okay, now from here it's striking at a distance of what? Capital S, we mark it as a range. So first of all, the velocity by which the liquid is coming out, we call it as what? Velocity of efflux, and that is under root of 2gh, basically the equation of kinematics. Alright, now what about the time taken by the liquid to reach? That is under root of 2 into capital H minus of small letter h upon g under root. Okay, fine. Now horizontal range, we have got the time, we have got the speed by which it is coming out, that will give s is equal to root of 4 times small letter h into capital H minus of small letter h. Alright, next one is time taken to empty the tank. Time taken to empty the tank. Here it's going to be t equals capital A divided by A naught into under root of 2h by g. And here what is A naught and what is capital A? What is A naught and what is capital letter A? Okay, capital A is the area of the container and A naught is the area of the orifice, which means here this is A naught and here this is what? A. Was that okay? Fine. And the final one is the volume of liquid coming out from the opening in unit time, again dV by dt, that is going to be V into A naught, where V is the speed by which liquid was coming out and A naught is the area of cross section. And in terms like if you replace capital V, definitely we are going to get it as what? Under root of 2 into G into H, where H was the height from the liquid level, isn't it? So there it's going to be what? A naught into under root of 2GH. Okay, so that was the rate at which the liquid was coming out. Fine. Next is viscosity. Fine. Whenever a body moves through a liquid, fine. So in other words, whenever a liquid is flowing over another body, there is going to be a force which is similar to that of what? Frictional force between the liquid and the body which is moving, or over the body where the liquid is flowing. That particular force is known as what? Viscous force. Alright. There viscous force F, that is equal to minus of eta times A into dV by dx, where dV by dx is known as the velocity gradient, A is the area of contact and eta is what? Coefficient of viscosity. Okay. So basically it's it can be marked in this way, like this is the liquid flowing. Okay, this is the liquid which is flowing. Now once the liquid is flowing like this, you all know that if it is a laminar flow, then different layer is going to have what? Different velocity part. So while flowing in the downward direction, okay, while flowing the downward direction, so this particular layer, that means the one which is on the top, that is going to have the greater velocity, and the one which is at the bottom, that is going to have zero velocity. So in that case, we mark the velocity like this. This is the maximum velocity. It will keep on decreasing like this, and the bottommost point is going to have what? Zero velocity. Okay, here I was telling about the movement of the layers. Okay, one will be sliding over the another one. Don't think that the lower bottom is having the maximum speed. No, the lower bottom, the layer which is connected to the surface, that is having zero speed, and the one which is at the maximum height, that is having the maximum speed. That is why dV by dx is negative, because while moving the downward direction, it's negative value. So the change in velocity of the body once we travel in the downward direction from the liquid surface, that is what we call it as velocity gradient. Okay, so I believe it is clear to you now. And what is capital A? Capital A is the area of contact, that means the area through which this liquid is spreading. Alright. And the next one is, okay, this is basically that what is dV by dx, what is going to be the SI unit, SI unit of coefficient of viscosity and all. So basically this particular relation need to be kept in mind, that is F is equal to minus of eta into A times dV by dx, where eta is coefficient of friction, A is area of cross section, not area of cross section, I am sorry, it's area of contact, and dV by dx is velocity gradient. Alright. And the next one is how the viscosity varies with respect to different factors. First one is about the temperature. Okay, whenever the temperature is increased, the viscosity what? Decreases. Okay, fine, for a liquid, and for a gas, whenever the temperature is increased, viscosity also what? Increase, and here this is that relation. Okay, and the next one is case of water. Okay, for water, viscosity decreases with increase in the pressure. That is, the next one is for pressure. That means viscosity of the liquid increases with increase in pressure. There we were telling about the temperature part, and here we are telling about what? The pressure. Okay, so for liquids normally it increases with increase in pressure, but for water it decreases with increase in pressure. And the next one is what is the reason behind the change in viscosity of gas with respect to increase in temperature. Okay. So, basically for the gas, the reason for this viscous force is diffusion, and whenever we increase the temperature, the rate of diffusion what? Increases. The rate of diffusion increases. That is why there is an increase in viscosity for the case of a gas. Was that okay? Now, let me tell you about what Poisson's formula or Poisson's equation. Basically, it tells about if I am having a horizontal pipe like this, where there is a steady flow is taking place, and here between these two ends there is a pressure difference of what? P, and the radius of this one is what? Small letter r, and the length of this pipe is what? Small letter L. Now, the rate at which the liquid will be flowing out, that is dV by dt, the rate at which the liquid will be coming out is going to be represented by the equation pi times P r raised to 4 divided by 8 times eta into L. This is the rate at which the liquid is going to come out. Alright, fine. And the next one is rate of flow of liquid, again the same thing, P by R. Alright. Now, where capital R is what? The Reynolds number. Reynolds number is not in the syllabus as of now. I just wanted to explain like what that particular relation can be. So, just for information I am telling, this is not in the syllabus. Now, what if the liquid is flowing through two different pipes connected in series as well as in parallel? Okay. So, here the pressure difference is going to be what? Basically, altogether the pressure difference is going to be the pressure difference across this one plus pressure difference across this one, that is P1 plus P2. Based on that, I can say that the resistance being experienced by the liquid to flow through this pipe is going to be what? R is equal to R1 plus R2. Alright, exactly same as that of the series combination of resistance. The same thing for what you can say, like the flow of liquid through two parallel pipes. So, here once they are connected in parallel, the pressure difference is going to be the same. So, the rate of flow of liquid, that means what volume of liquid is coming out of the pipe in unit time, that is rate of flow. So, there the rate of flow is going to be what? Here, if through this pipe if it is V1, and if through this pipe if it is V2, then the total rate of the liquid coming out through the combination of both, it is going to be V1 plus V2. So, based on that, I can say that 1 by R, that means the equivalent resistance offered against the flow of the liquid is going to be 1 by R equal to 1 by R1 plus 1 by R2, and in this case remind you one thing, the pressure difference is what? The same. Okay. The next one is Stokes law. The Stokes law says, if I have got an arrangement like this, I mean a vertical column, and I am having a spherical body which is allowed to fall freely like this. So, there the viscous force experienced by this particular body, it is going to be F equals 6 times pi into eta times R into V. 6 pi eta R into V, where R is the radius, V is the speed by which it is going down, and eta is coefficient of viscosity. So, if it keep on moving like this, okay, and if it is inside the liquid, definitely we know that there is going to be what? A buoyant force also. Okay. So, at a time 3 forces are acting. First one is its weight acting the downward direction, that is mg. Next one is the viscous force F suffix v, that we already marked, and here this is not a force, I was telling about the speed by which it was coming down, and the third force is buoyant force F suffix b. Okay. Now, at equilibrium, F suffix v plus F suffix b, that means the viscous force as well as the buoyant force, it is going to be same as that of what? Mg. Then there won't be any further increase in the speed by which this ball is coming down, and that maximum speed is known as what? The terminal velocity. Okay, fine. And the terminal velocity v is going to be 2 times r square into rho minus rho sigma into g all divided by 9 times eta, where rho is density of the material and sigma where rho is the density of the body, I mean that particular, I said it as density of the material, okay, rho m, or you can say it as rho, and sigma is the density of the liquid. Alright. And now some special cases, like what if rho is greater than sigma, that means the density of the material is greater than the density of the liquid, definitely it will fall in the downward direction. Next one, what if rho is less than sigma? So instead of body move in the downward direction, it will be move in the upward direction, because the weight is lesser comparatively. So this will be forced to move in the upward direction. And third one is, what if sigma is very less than rho? Just have a look at this. If sigma is very less than rho, what will happen? This particular part will be approximately equal to rho only. You can see the same thing here. Okay, and here this is terminal velocity versus time distance graph. Okay, so after a particular time, I told you the velocity is going to be maximum. Now beyond a particular time, the velocity won't be increasing, and of course while traveling down, though the distance traveled by the body is keep on increasing, but the speed remains the same. So that particular graph also must be there in your mind for sure. Next one is critical velocity. I think I already told you that particular velocity at which the streamline flow is all of a sudden got converted into turbulent flow, that is known as critical velocity. Just you must know what is critical velocity, that is all. And now we are moving to the next, that is surface tension. Basically the force exerted by the liquid per unit length is known as surface tension, that normally happens at the surface of separation between two medium, like for air and water, you can say. Fine. So here of course the dimensional formula as well as the basic equation is there. What is the basic equation? Surface tension S is what? Force per unit length. Alright. Now few important points. Of course first is its unit, that is Newton per meter. Okay. Next one, it is a scalar quantity. It's a scalar quantity. And now comes what all are the cases, what all are the factors, or like basically a small briefing regarding the surface tension. So there, in order to explain that, we need to explain about what? Adhesive force as well as cohesive force. So adhesive force means the force between, like for example let this be glass and this be a liquid. Now the molecule which is close to the glass, which is the very first layer of molecules which is directly in contact with the glass, they are experiencing force due to the glass, force of attraction due to the glass molecule, and definitely due to the surrounding molecules of the liquid itself. So the force between molecules of liquid, that is known as cohesive force, and the force of attraction between molecule of glass and the liquid, that is known as what? Adhesive force. So where adhesive force is greater than cohesive force, the meniscus is going to be in this way, and where the cohesive force is greater than adhesive force, the meniscus is going to be in this manner. Alright. Next is how we can represent the surface tension of different arrangements. Okay, and there itself, what is going to be the net force experienced by a different type of structures that is floating on the liquid, or once we try to lift it off from the liquid surface, what is going to be the net force experienced by different arrangements. So here the first one is a thin ring of radius capital R. So we are having a ring like structure, okay, like a wire into a perfect circle, molded into a perfect circle, that is kept on a liquid surface. So we just make that ring touch on the liquid surface and we are lifting it. Okay, so ring like structure is there, it's just touching the liquid and we are trying to lift like this. So you can see a shape of, that means this liquid will be trying to get raised along with the liquid. Okay, now here altogether the length is what? 2 pi r. 2 pi r into s, that will be the net downward force. Okay, 2 pi r into s will be the downward force. 2 pi r into s, that's going to be the downward force. Now you must understand one thing, here one force is there as well as on the inner surface also, then one more force is there. So how much is going to be? 2 pi r into s again plus 2 pi r into s. Alright, so you can see 2 pi r into s plus 2 pi r into s, so definitely r plus r is there. Fine, so s is common, that's why we took it as 2 pi into r plus r. So now other than that, weight of the body is there. So the net downward force acting is going to be 2 pi r into s plus 2 pi r into s plus w, and that is going to be balanced by the upward force. Alright, so that was a ring, so that's why we have two contacts. I repeat once again, we are having an inner surface and we are having an outer surface. So on both the sides the force will be experienced. So that is why it is 2 pi rs plus 2 pi rs. Now next one is a circular plate of disc, circular plate or disc. Here there is no two layer case of two layer is not there, we are having only a disc. So only on one separation, surface of separation is there. So here we are having two surface of separation, and here we are having what? Only one surface of separation. So there it is going to be 2 pi r into s plus w, and it is a square frame now. So it is a square frame, that means here you are having one surface and here you are having another surface, just like as that of what? As of ring. So it is going to be 8 times a into s plus w, where a is the side. Okay, so here this is a plus a, that is 4a into s inside and 4a into s outside. So that is why it is 8a into s plus w in the downward direction, need to be balanced by capital F. So you might be wondering how the questions will be asking. Definitely it's going to be what need to be the force that we need to apply to lift it off from the surface of the liquid. That is the question is going to be. I believe it is clear now, isn't it? So the next is a square plate, there it is going to be 4as plus w, and next one is inner disc having radius as r1 as well as r2, the concept is the same, it's going to be 2 pi into r1 plus r2 into s plus w. Next one is a wire of length L, there we are having two edges, here one surface is there, there also another surface is there, that is why it is going to be 2 times L into s plus w, that is going to be the weight here. Alright, and next one is the factors affecting, fine. So few factors I have mentioned over there, so better you just go through this fact, or like what are the factors affecting the surface tension, because you know why I added all these points is I told you in the beginning itself, there are cases where match the following as well as assertion reason types. These theoretical points are very important. Okay, so you please take a pause and go through this all points. Okay, make it thorough. Next one is surface energy. Basically the work done in changing the surface area. Surface area is stored as the surface energy. Alright. So whenever, like for example, I can consider the case of a air bubble, alright, or you can say a soap bubble, alright, or you can say a balloon, which is we are blowing a balloon to increase the volume, I mean, so we are trying to make it more bigger. In all those cases, whatever the energy that we spend to increase the surface area of that one, that we call it as what? Surface energy. And how we calculate surface energy? If surface tension is given as capital S and change in area is given as what? Delta A, then the surface energy is going to be what? S into delta A. S into delta A is going to be the surface energy. Okay, now next one is work done in blowing a liquid drop, okay, whose radius is increasing from r1 to r2. Very simple. Initially it is having a surface area of 4 pi r1 square. Now it is having an area of 4 pi into r2 square. So what is the change in surface area? 4 pi into r2 square minus r1 square multiplied by s is going to be the work done. The same principle is used here as well for the soap bubble, but for the soap bubble the thing is that was liquid drop and here this is soap bubble. So soap bubble is having two surface of separation, 1 and 2. Okay, so that's why it is 8 times pi into r2 square minus of r1 square into s. And the next one is work done in splitting bigger drop into n number of drop. Then so there were questions based on this. Important area, I repeat, important area. There were questions based on this, and definitely like here also blowing the air bubble as well as blowing that liquid drop everywhere, increasing the changing the surface area of all these cases. There were questions. So now here it is. A bigger drop is splitted into small letter n number of drop. Okay, now understand one thing. Capital R is the radius of the bigger drop and small letter r is the radius of the smaller one. So mass is conserved, so definitely volume need to be conserved. Alright, so 4 by 3 pi r cube, that is going to be n times 4 by 3 pi into small letter r cube. So this particular relation will give the relation between capital R and small letter r. Okay, so what's going to be small letter r now? small letter r is going to be n raised to 1 by 3 times capital R. Okay. Now the work done is going to be 4 pi s into n times r square. How come that be? Surface area of n number of smaller drops, isn't it? So the 4 pi came out. So n times r square minus of capital R square, that gives the work done. Okay. The same thing, that means the reverse of that is going to be small n drops of radius small letter r, small n number of drops or small letter r combined together to form a bigger drop. Exactly the reverse of this will give the work done. Alright. Next one is excess pressure. Basically, you must understand one thing. I am having a chamber like this, a thin membrane is here. I am having pressure here as P1 as well as pressure here as P2. If P1 is P2, this thin membrane is going to be straight. And if P2 is increased, I repeat, if P2 is increased, what happens? The membrane is going to take a shape like this. Here P2 is greater than what? P1. And if P1 is greater than P2, then the membrane is going to change like this. So here P1 is greater than what? P2. Alright. Now based on the surface tension of that separation, we will be able to calculate the excess pressure. Excess pressure means here P2 minus P1 and here this is P1 minus P2. So excess pressure we normally mark it as what? Delta P. Here this is P2 minus P1 and here delta P is what? P1 minus of P2. Okay. Now case number 1. For a liquid drop, it's going to be 2s by r. For air bubble, it's going to be, for a excess pressure inside the air bubble, it's going to be 2s by r. Alright. Now for soap bubble, it's going to be what? 4s by r. So here this is liquid drop and here this is air bubble and here this is what? Air bubble means, you must understand one thing, air bubble means water and here this is air. Alright, so only one separation is there, that is why. Here this is soap bubble. Soap bubble means, see, here this is air, here this is soap and here this is air. So surface of separation is 2, that is why it is what? 4s by r. Alright. Next one is excess pressure in different cases. Okay, so here this is a plane surface, so the excess pressure is going to be what? Delta P. I think you are having a rough idea, like based on this, I think you will be able to connect here. Now for a convex surface, of radius r like this, it's going to be 2s by r based on the surface of separation only. For concave surface also, it's going to be 2s by r, but here the pressure outside is greater than pressure inside region. Now when two bubbles of radii r1 and r2 coalesces, then the radius is normally, that means if this is an isothermal process, there is no temperature change, then r is going to be r1 square plus r square is going to be r1 square plus r2 square. They were question based on this. And the next one is, the common interface radius. There 1 by r is going to be 1 by r1 plus 1 by r2, or it can also be written as r is equal to r1 r2 divided by r1 plus r2. Next one is angle of contact. Like for example, here we are having a a container in which we are having water and glass is dipped and we are just trying to pull it in the upward direction. So definitely there you can see a shape in the surface of the liquid like this. So if I draw a tangent in this way, this particular angle is known as what? Angle of contact. Alright. Now there are a few important points regarding angle of contact. What are the factors and how it will be affected based on the adhesive force, adhesive force as well as coercive force. That is a very, very important point. Okay. And here this is going to be angle of contact for few materials, like for glass, for mercury and glass combination, water silver combination, alcohol and clean glass combination, like that. Few angle of contact cases are there. Okay. And main thing, how the angle of contact depends on the impurity. Okay. So the thing is, whenever we add impurity, what will happen? The angle of contact decreases. Another one is, what about the temperature variation? Okay. The angle of contact increases with temperature of the liquid, variation in temperature. Alright. Next is capillarity. So here what basically capillarity says, let me consider a liquid like this. and let me consider a narrow tube. Let me make it as a tube of radius say small letter r, not that narrow. Now what you can see is the liquid column, it will be raised through a particular height. Okay, it will be raised through a particular height. Okay, the liquid will be raised to a particular height. I can say this as h. So this happens comparatively in the case of a narrow tube. Okay, so if r is the radius of the tube, okay, s is the surface tension and theta is the angle of contact, fine. Now rho is the density of the liquid. Now the height through which this particular liquid can be raised, okay, that is going to be h equals 2 times s cos of theta all divided by rho rg or rho gr minus of r divided by 3. And if it is very narrow, that means the radius of that tube, which is known as a capillary tube, that is comparatively a smaller value, then r by 3 is approximately going to be what? 0 value. That means r is very less compared to that of 3, definitely it is going to be 0. In that case, we can write as what? H is equal to 2s cos theta into rho rg or r rho g. Alright, so this is how we calculate the capillary rise. Okay, now the capillary rise depend upon S, that is surface tension, theta, that is angle of contact, r, that is the radius, rho, density, and g, acceleration due to gravity. Alright, fine. So that was here all about hydrostatics as well as hydrodynamics. Next chapter is Kinetic Theory of Gases, in short KTG. Okay, so here first of all I want to tell you what is kinetic theory of gases. So of course, while studying the behavior of gas, we know that there are two types of properties, microscopic as well as macroscopic properties. So whenever we try to define the macroscopic properties of gases, it was found that it's mandatory to study how the gas behave in its microscopic level. Okay, so the study made for that and the conclusions based on microscopic study of the gas to define the macroscopic properties is known as what? Kinetic theory of gases. Now let us see what were the conclusions of that study. The first point says every gas consists of extremely small particles known as molecules. Okay, and the important point is the molecules for a given gas, it's going to be what? Identical. Okay, for a given gas it's going to be identical, but definitely it's going to be different for another specimen. I mean, for another gas, another type of gas, the molecules is going to be different. Okay, so molecule of A and molecule of sample B, definitely it is going to be different, but all the molecules of sample A and all the molecules of sample B, they are going to be what? Similar. That is the first point. Second point is about the shape and their behavior. The shape of the molecules is treated as spherical, and I already told you it's similar, that's why it's mentioned as identically spherical. Point number 2, it is rigid, and third one and the most important, that is perfectly elastic. Okay, definitely the size is very small, that's why point mass, and you can see the average size. Okay, now here the molecule size is negligible and the comparable average, the distance of separation is treated as was 10 to the power minus of 9 meters. That is the average distance of separation. Now the speed of the molecules, I repeat, the speed of the molecules depending upon the temperature, it can lies between 0 to infinity. Lies between 0 to infinity. Moving to the next slide, the distance between two successive collision, the average distance of separation between two successive collision, that is known as what? Free path. And the mean of all these free path, it's known as what? Mean free path. This is a very important point. Questions were there many a times regarding this one. Now the next point, that is point number 6. Point number 6 says there is no attractive force between the molecules. Okay, and point number 7, see, point number 7 is basically, point number 6 only, like it's given in depth. That means, see, what they say is in point number 6, there is no attractive or repulsive force acting between the gas molecules, isn't it? So, point number 7 confirms the same, even you need to ignore the gravitational force of attraction also. Okay, fine. The next one is, if you consider the density of a gas, all these points are very, very important while dealing with the studies ahead. So, whenever we consider the density, we need to take it as uniform throughout the sample. Alright, and the last one is regarding the motion. Okay, the gas will try to move in all possible directions. So, we can say that it is in random motion. It is random motion. That means immediately after the collision, we can't predict in which direction it will be moving. It can move in all possible directions until or unless it doesn't face any obstacle across its path. Okay. Now, few laws based on the study of behavior of gas. That is what known as what? Gas laws. Out of that, the first one is Boyle's law. Okay, Boyle's law says when temperature is kept constant. Okay, in Boyle's law, T is kept constant. When temperature is kept constant, okay, volume is inversely proportional to pressure. Volume is inversely proportional to pressure, and or you can say PV equal to a constant. So here in Boyle's law, temperature is what? Constant. Okay, and next one is Charles' law. Okay, Charles' law says at constant pressure, okay, volume is directly proportional to temperature. That is Charles' law. All right. The next, also of course, graphical relations are very important. So here it is inverse relation. So we proportional to 1 by P. So the graph is going to be rectangular hyperbola, and here V is directly proportional to temperature. So it's going to be a straight line. Okay, and here you need to identify this particular point. So here once temperature is 0, the volume is what? V0. And if you want to decrease the volume to 0, okay, which is practically not possible, so we will be extending it in the backward direction. Okay, fine. So this is that extended portion. So this dotted line says if this variation was keep on continuing like that, then definitely what? It should have been, the volume should have been 0. But if a gas is there, and if you keep on compressing, keep on reducing the temperature, like keep on reducing a dot, if volume 0 means what? All of a sudden the mass will disappear, isn't it? So this is just an extended portion of that only. So just try to understand how the graph could be like explained for the variation of volume as well as temperature. So of course the next one is Gay-Lussac's law of gaseous volume. Okay, here we keep volume constant. We keep what? Volume constant. And if volume is constant, I repeat, if volume is constant, then pressure P is directly proportional to temperature. Pressure P is directly proportional to temperature. Now please try to understand all these cases. Okay, the very first one, like Boyle's law. Here the temperature was constant. Temperature was constant means whatever changes we are making to the system, okay, there is no temperature change happening. That means whatever the changes happens, immediately there is a heat exchange taking place, and as a result of that, the temperature of the given sample remains what? Constant. Okay, fine. Now second case, here the pressure was kept constant. Okay, like in this case we can imagine something like this. A specimen is there and it has got a movable top. So whatever the changes we make to the specimen, to the sample, then what happens is that container itself will adjust to maintain the pressure of the gas to be constant. Okay, like a movable piston you can say. And here the third one, constant volume. Here it's completely trapped. Okay, that means the lid is tightly closed or the piston is locked, anything you can imagine. Okay, that is what they mean to say, but pressure is kept constant. Sorry, volume is kept constant. So if volume is kept constant, then how the pressure will vary with respect to temperature? More the temperature, more will be the pressure. The same variation you can see here, exactly as that of what? Vt relation, you can see Peter relation here. So here in Charles law as well as in Gay-Lussac's law of gaseous volume, okay, this graph is what? Straight line. Here this is PT graph, here this is Vt graph, and here this was what? Boyle's law. Here V is inversely proportional to pressure P. Alright, and now let's move to Avogadro's law. Avogadro's law says that, okay, under equal value of pressure and temperature, all gases will be having same number of molecules present. Okay, that is what Avogadro's law. And he defined that with a exact value, okay, for a given volume and for a given temperature, that is 22.4 liter of each gas at STP. Okay, will be having 6.023 into 10 to power 23 molecules. We call this number as what? Avogadro number. Okay, exactly the same thing I told you. If pressure, volume, temperature is same for 3 sample, okay, then the number of molecules present in all the 3 samples will be the same. Okay, and here we define a standard volume and temperature as well as pressure, and we are giving the number of molecules present there, that is 22.4 liter of each gas at STP is going to have 6.023 into 10 to power 23 molecules present over there, and this number is known as what? Avogadro number. Now next is Dalton's law of partial pressure. Okay, so if I am having a container like this, okay, here a sample of gas named A was added and the pressure exerted due to that gas is P1. Now on the same on the same container, this time I am giving another sample, I am adding another sample, this is completely removed, and I am adding another sample, and that is B, and the pressure exerted due to that one is what? P2. Now if I consider the presence of both the samples in the same container, like now A plus B is there. Now altogether the pressure exerted by these 2 samples together in the same container under same conditions, it's going to be P equal P1 plus P2. And if I have got n number of samples, okay, then the total pressure is going to be P1 plus P2 etc. up to Pn. That is what? Dalton's law of partial pressure. Okay, you must understand the situation. I was having a container, and in that container I consider a gas of sample like A, I can say, and the pressure due to that one is P1. Now it's completely removed. Okay, now on the same container under same conditions, this time I am going to have another sample, that is B. Now the pressure due to these samples is P1 and P2 separately. Now both the samples, I mean both A as well as type B gas is filled in the same container under same conditions, I mean the temperature, then the equivalent pressure, the total pressure is going to be what? P1 plus P2. I believe it is clear for you. Next one is ideal or perfect gas equation. We know the relation, that is what? PV equal to nRT or PV equal to mu RT. Okay, now this particular relation obeys all the laws what we discussed here, starting from gas law, starting from Boyle's law, followed by Charles law, then Gay-Lussac's law and Avogadro law. All these laws are being obeyed by this particular relation, and the relation says that PV equals mu RT or PV equals nRT. Okay, I prefer this particular relation basically because in many of the textbooks, small letter n is treated as number of molecules per unit volume. So I recommend this relation to avoid confusion. Okay, it's my choice. You can go for any of these two. No worries at all. All right. And yeah, of course, see, what was Boyle's law? Boyle's law says that when temperature remains constant, P is inversely proportional to volume. See, just try to understand it. Keep this as constant. Now P is inversely proportional to what? 1 by V. Isn't it? And what was Charles' law? Charles' law says that when pressure remains constant. Now let's consider P as constant. V is proportional to what? T. Okay, and if volume is constant, Gay-Lussac's law, if volume is constant, then P is proportional to what? T. Fine? Are you able to connect that? Yes. That is ideal gas equation or perfect gas equation. Next is pressure exerted by a gas. So for this, what I am going to do is, let me consider a container like this. Okay, and gas is filled. So you know that once we have got a gas and it is kept in a container, the volume of the container is going to be the volume of the gas. Okay, and so volume of the container is capital V, so V is going to be the volume of the gas. Okay, now let me take small letter m. Let me take small letter m as mass of one molecule. I repeat, mass of one molecules, and let me take small letter n here as the total number of molecules. Total number of molecules. I told you small letter n, in some textbooks they may consider it as what? Number of molecules per unit volume also. So here small letter n is marked as what? Total number of molecules. Okay, fine. Then the pressure exerted by the gas is going to be P equals 1 by 3 into mass of one molecule, that is m, into total number of molecules n, all divided by V into V bar square. Here V bar is treated as RMS speed. And what is RMS speed? Let us consider n number of molecules are here. Okay, now V1 is taken as the speed of particle number 1. Particle means molecule. Now V2 is speed of molecule number 2, and Vn is the speed of the nth molecule. Then V1 square plus V2 square etc. up to Vn square divided by n, the all root is known as what? Vrms speed. So here V bar is stated as the Vrms speed. Now here this is mass of one molecule. Small letter n stands for total number of molecules. Now m into n, that's going to be the total mass. Total mass by volume, what it is going to be? It's going to be density. So you can see m into n by V is replaced by what? Rho. Alright, so here comes the two relations, okay, for pressure, and I recommend you to memorize this. Pressure is 1 by 3 times rho V bar square. Okay, from here you can easily jump to this. Okay, though I started with this and moved to this one, I recommend you to memorize this if possible, because that is easy to understand, and definitely from this you can easily move to this particular relation as well. Okay, now for 1 mole of a gas, definitely capital this small letter n, it's going to be Avogadro number, and there this is going to be mass. This is going to be mass of 1 mole of a gas. We call it as what? Molar mass. So that relations come here as again 1 by 3 into capital M it is. That's all. That is the only thing. So I told you can memorize this one, and from here you can move on to anything. Regarding this, the RMS speed we already discussed. Okay, the next one is the pressure of the gas in terms of kinetic energy. It's very easy. See, what was pressure? Pressure was 1 by 3 into rho V bar square, isn't it? Now have a look. 1 by 3 into what was this? Density. Density is mass, okay, total mass, and here total mass was what? Small letter n into small letter m, that was total mass, by volume into V bar square. Here this is the total mass. isn't it? Now let me multiply this with 2 and divide this with 2. So here half of n into m into V bar square, okay, into 2 by 3 is going to be the pressure. Okay, now please tell me, what is this? This is the total kinetic energy, isn't it? So here I can say 2 times E, where E I am taking as the total kinetic energy. 2E by 3 is what? Pressure P. Okay, so again I confirm you need to keep this particular relation only. Easily you can move on to this. Okay, the next one is average kinetic energy. Average kinetic energy per molecule. So here this is average kinetic energy per molecules. It is 3 by 2 times K suffix B into T. I repeat, 3 by 2 times K suffix B. Here it is marked as K, Boltzmann's constant, into T. And now here this is average kinetic energy per mole of a gas. Here this was for what? 1 molecule, and here this is for 1 mole. It's very easy to connect, because for 1 molecule it is E is equal to what? 3 by 2 kBT. And if it is for 1 mole, so of course this is for 1 molecule, so you need to multiply it what? N suffix A, Avogadro number, and K suffix B multiplied by N suffix A, Avogadro number, what it is? Capital R. So that is what relation is. Alright, now how kinetic energy is connected to temperature? Of course directly proportional to absolute temperature, means temperature in Kelvin scale. Next one is root mean square speed. Okay, see here I will tell you something very important. What was the relation here for kinetic energy? The relation for kinetic energy was E is equal to what? E is equal to 3 by 2 R into T, isn't it? Now please try to understand it over here. We know half of m into V square, that is what? The kinetic energy here, isn't it? Now what was kinetic energy in terms of energy value? We got it as 3 by 2 R times T for 1 mole of a gas, isn't it? 3 by 2 RT. Now if I go for that, 3 by 2 times R into T, that was energy, isn't it? Now in terms of what? Capital R, how we explain the kinetic energy? This one, 3 by 2 RT, isn't it? Now just rearrange this. While rearranging this, you will get the value of V, I mean the RMS value, as what? 3 times R into T upon M, the under root, isn't it? Because 1 by 2 and 1 by 2 will cancel each other. Fine. So finally it's going to be what? 1 by 3 term is going to be there. So that is 3 RT by M. Okay. Now keep this particular equation in mind. The average value V RMS is under root of 3 RT by capital M. 3 RT by capital M. You please keep this equation in mind, because it is very important onto many factors. Alright. Now keep this in mind. Now comes the next one, the average speed. What it is? Average speed. So V RMS, what was the relation for V RMS? It was under root of 3 RT by M. And once it is average speed, the changes happens is, this 3 will become 8. 3 is going to be 8. So it's going to be 8 RT divided by, along with M, it's going to be pi times M. That's going to be the average speed. Alright. And the next one, that is the most probable speed. You need to keep this equation in mind. For the most probable speed, 3 is going to be replaced by 2. That is the relation. Okay. Once you know this, you can easily move on to the next one. Okay. So V RMS, that is under root of 3 RT by capital M, where capital M stands for molar mass, and average speed, it was average speed, then it is going to be under root of 8 RT by pi into capital M. The last one is most probable speed. Most probable speed, there it is going to be root of 3 is going to be replaced by 2. 2 RT by capital M. It's very easy. Okay, so try to keep any one standard equation and that will help you to connect with the remaining. Next one is mean free path. We already discussed what is mean free path in the beginning. Okay, the mean of the free path. And what is free path? The distance between two successive collision points, isn't it? Fine. So there mean free path is represented by letter lambda, and there it is going to be Boltzmann's constant k suffix b into t all divided by under root of 2 pi into t square times p, where p stands for what? The pressure. Alright, and the next one is degree of freedom. Okay, the degree of freedom is basically the number of independent ways in which a particle can move. That is degree of freedom. The number of independent ways in which particle can move. And here the particle means molecules. Particle means what? Molecule. Okay, now here I am going to represent it in small letter f only, and the relation regarding this one, degree of freedom, it is very very important. Yeah, of course. I want to tell you something regarding the mean free path. See, please try to understand. It is root of 2 pi into d square times p. Okay, I made a mistake here. Under root of 2 into pi times d square into p, where d stands for the diameter. Alright, now yeah, what I mean to say is, once we are onto the discussion regarding the mean free path. Okay, so here this is collision number 1 and here this is collision number 2. This value is going to be what? Lambda. Fine, and we know the average speed also. Now lambda divided by that speed, that will give what? The time gap between two successive collision, and we call this as relaxation time. What? Relaxation time. We call it as relaxation time, and that is going to be represented by letter tau. Alright, and the number of collisions happens in unit time. That tells about what? The frequency. Okay, so that particular relations are also important, but once you know the value of lambda as well as v, you can easily get onto that. It's not a big deal. Now, of course, what about the degree of freedom for different type of molecules? For monoatomic molecules, degree of freedom is 3. For diatomic molecules, it is 5 because 2 translation motion and 2 rotational motion. The non-linear diatomic, there it's going to be what? 6. That is 3 translation motion and 3 rotational motion. And the next one is linear triatomic. Okay, there it is going to be 3 translational, 3 rotational and 1 vibration. Alright, the next one is about specific heat at constant volume and specific heat at constant pressure. Questions were there regarding this one. Okay, so specific heat at constant volume, that is going to be F by 2 times capital R, where F is degree of freedom. Okay, next one is Cp, specific heat at constant pressure. There it is going to be F by 2 plus 1 into R. Basically the thing is Cp minus Cv is equal to what? R. You have to keep only this relation in mind. Cv is equal to F by 2 times R. I repeat, Cv is equal to F by 2 times capital R. Okay, now to get the value of Cp, you can put the value of what? Cv here. It's going to be what? F by 2 into R only. You can take that towards the right. That's it. Okay, next one is the relation between gamma. Gamma is the ratio of Cp by Cv and degree of freedom, and gamma is equal to 1 plus 2 by F. Okay, next one is for monoatomic gas, diatomic, linear, polyatomic or non-linear polyatomic gas, how you value, that is the internal energy, Cv specific heat at constant volume, Cp specific heat at constant pressure, and gamma is going to be. Okay, these relations are very very important. For monoatomic, the energy is going to be 3 by 2 RT. Again I repeat, I recommend this particular relation and this relation. So if you know about this relation like Cp minus Cv is equal to R, what is U, okay, you can reach on to the remaining all relations. I will tell you how. See, this is about the internal energy. The internal energy for 1 mole of a gas is going to be 3 by 2 RT, okay, where 3 is degree of freedom here, and here this is diatomic, there the degree of freedom is what, 5, and here this is non-linear polyatomic, there it is what, 3 RT, okay, fine. Basically it is 6 times RT by 2, that is why it is 3 RT, degree of freedom is 6, so 6 by 2 it's going to be 3 RT, is that fine? Okay, now so degree of like total energy, that is represented in terms of degree of freedom, and degree of freedom is replaced by 3 here, 5 here, as well as 6 there, and finally it is there as 3 RT. Next one is Cv. Cv is du by dt. Like if you differentiate this with respect to temperature, you will get what, Cv. So you can see here, it was 3 by 2 here, it is 3 by 2 RT, it is 5 by 2 RT here, 5 by 2 R, it is 3 RT here, it is 3 R. So that is Cv. Now Cp minus Cv is equal to R, isn't it? I repeat, Cp minus Cv is equal to R. So what is going to be Cv? Cv is going to be Cp minus of R. So you can see here, it is 3 by 2 RT minus of R. So you are going to get it as what? 5 by 2 R. Alright, fine. Now the next one is for diatomic. Okay, there it is going to be 7 by 2 times R, and the next one is non-linear polyatomic, it is 4 times R. Okay, and the next one is, have a look, we need to get the value of gamma now. We need to get the value of gamma. And what is gamma? Gamma was Cp by Cv. Now we know the value of Cp and you know the value of what? Cv. Alright, so Cp is given as what? Cp is given as 5 by 2 R and Cv is given as what? 3 by 2 R. Just take the ratio, you will get these values. It is as simple as that. Okay, now regarding degree of freedom, I already told you the relation is gamma is going to be 1 plus 2 by F. So if gamma is given, you can easily calculate degree of freedom, or if degree of freedom is given, you can easily calculate what? Gamma. Okay, I repeat once again, I personally recommend this relation. Differential of this is going to be here, this one, and Cp minus Cv relation is Cp minus Cv is equal to R. You will get that one. And finally, if you want to connect up to the relation associated to the degree of freedom as well as gamma, then gamma is equal to 1 plus 2 by F. Okay, and next one is law of equipartition of energy. Okay, the law of equipartition of energy says, if we consider a specimen, a sample of a gas, and the energy possessed by, the total energy possessed by is capital E. The total energy possessed by a molecule is capital E, and the degree of freedom is F. Degree of freedom is F. Then for one particular degree, the total degree of freedom is F. Okay, and for along one particular direction, that means just because of the translation motion, I am just telling an example, just because of translation motion only. Okay, what is going to be the energy possessed? Definitely it's going to be translation motion along x-axis, translation motion along y-axis, as well as translation motion along z-axis. Okay, now if this particle is having 3 degree of freedom only associated to translation motion, and say 2 degree of freedom associated to rotational motion, so the degree of freedom is what? 5. Now along x-axis, just because of translation motion, I repeat, along x-axis, just because of translation motion, the energy possessed by that one is going to be E by 5. E by 5. This is basically what law of equipartition of energy says, and let us see what that definition says. The law states that for dynamic system in thermal equilibrium, the total energy is distributed equally amongst all degree of freedom, isn't it? So here I told you degree of freedom, if it is 5, then the energy along that x-axis, just because of the translation motion, is going to be what? E by 5 only. See, distributed equally among all the degree of freedom. Alright, so that was all from my end related to this particular module. We will meet you soon with the detailed discussion related to another set of chapters. Till then, bye bye and take care.